I don't know, probably not. So I should do that.
Hello, hi, my name is Filippo, and tonight I'd like to talk about blending. So I would like to talk about blending data structures. So it was just an experiment that actually I did a few times ago, like a couple of months ago, and I would like to start with a list. And a list, this is like a partial hierarchy of list, and list is like is a traversable, and traversable has this plus plus operator. I'm wondering, maybe this is what I need for blending. So when I want to blend two lists, maybe I want to use that plus plus operator. And what I'm expecting when I'm blending two lists, I'm expecting maybe to append one list to another one. This is the definition from the Scala doc. So yeah, that's fine. Plus plus is good. I can append two lists together. That's blending for me. It's fine. Let's look at another data structure. Let's look at set. Again, set is traversable. And so we have the plus plus operator. And what's happened with sets? This is the definition. It's slightly different. For sets, that plus plus is like adding sets, two sets together. And this is the expect output, of course. Yeah, we get all the elements from both sets. And of course, a set can't have repetition. Okay, so that's pretty straightforward. Plus plus looks like the blended thing that we're looking for. We have a dark gray smartphone we put in the blender, and we get dark gray hashes. So far, so good. Here comes map. Map is a traversable. So it has the plus plus operator. And the definition from Scala doc is exactly the same as set, exactly the same. So I'm expecting to add maps one to another one. And that's fine when the one of the map is empty. Let's say we have this map, a map of sets. And we have two sets as value. And what are we expecting here? Like, according to the, actually we know what's going to happen, but I would like to ask you what's going to happen. We could have one of these options, right? The last two are like bogus, like runtime exception, compiler, everything is fine, type is fine. So we could have one of these options. I don't know what you think is the one. Anyway, I'll tell you. It's this one. Why? So why we get this value? So basically, we get the value, the right operand, no matter what. So when we use the plus plus on map, that's fine. We get the right operand. So basically, we get the value when we have a key collision of the right operand. Okay? So yeah, that's blending. Yes, but you know what? That's my world. I want to blend the way I want to blend. So in my world, when I mean blending, I don't want dark hashes. I want that. I want those sets to merge together. Because that's my word, do whatever I want, okay? So when I have this iPhone C, I put it in the blender. I know I get dark hashes, but I want rainbows, okay? we know how to implement this, right? We are developers, we know how to implement this. We get two maps. These are the type signatures. Again, maps, we forget about the key, it doesn't matter. The value is a set of int, okay? This is our reference data structure. Like, same example. This is what I want. I want like to implement the logic that gets those two elements from the two operands and apply the plus plus operator from the traversable. And this is the result I want. Okay, now, just for didactic purpose, we're going to implement this in a mutable way, okay? In a, let's say, imperative way, okay? I know we shouldn't do it, but this is didactic, okay? So this is the type signature. So I'm having the two maps here, immutable, of course. And then, because I want to do this in an immutable way, I'm using like a for in the middle of the implementation. That for is basically looping over the second map. That's one implementation. To the second map, and what I want to do is basically merging those maps together, and if you have the same key, the value should be merged. What's wrong with the for? Nothing yet. 1 second. So before looking what's wrong with the for, we should see that because the maps are immutable, I need to convert to a mutable map, and then I need to convert back to mutable because I'm returning an immutable map. Okay. But I was saying, what's wrong with that for? There's nothing wrong with that for, but to be honest, inside this logic here, there must be a side effect. So if we have this for, no matter what, we need to have something from outside. So in other words, outside that for, we need something, or a value of a mutable collection, or we need a variable. There's no other way. And what's happening inside that for must mutate something outside if you want a result, if you want a side effect. Therefore, the for each. So it was very complicated, but at the end of the day, that for each is for everybody and my future self to tell me, you know what, there's some side effect here on something outside that for. Okay, so far so good. This is an implementation. Okay, pretty straightforward. I'm adding the two sets, otherwise I'm adding the element from MB into MA. Result, and I get the result. This is the first correct implementation, okay? Imperative. Now, let's do an immutable version of the same logic. So, what is this? This is basically a fancy way to do a fold left. So if you're new to this symbol, it's basically a fold left. So we are folding the second map, like very similar to what we're doing there, but we're accumulating the result here. So that could be an implementation, an immutable version of the same implementation. Another word about the symbol there, why they make this funny symbol, like how can you read that as fold left? Simply because I read some answer on a group that should look like a domino tiles, where the first tile should be like the seed of the fold, and then you can. So that's the only way I can remember about that symbol. So when I write Scala code, but it's nothing else than a fold left like that. Okay, so we have our immutable version of the implementation, and let's do a little refactor here. There are some common parts. There's a check on this contains, and we're gonna get the result. So let's refactor this way. In other words, let's get the result. That will be an option, and then we pattern match on the option. Okay? It's exactly the same implementation. All good? Now, few options here. Okay, there's nothing wrong with the pattern match, but come on, Scala is cool because you can write concise code. So let's just refactor those 3 lines. We can call map and then get Rails and do exactly the same thing. Or if you have Scala Z, if you import Scala Z, you can import like the option goodies. You can call this shorthand. Very useful. You can say, okay, in case of some, I run this. In case of none, I return that. Or in I think Scala 2.10 or Scala 2.11 on map is on on immutable map we have fold, but it's very cryptic, so I will just keep going with that. And then if you want, you can have a catamorphism. Again, you need a Scala Z in order to have that. It's very ironic because there's a Stack Overflow question that I read like probably last year, and there's Barton Odesky saying that, oh, you know what? When I have this kind of situation, I like to have a map in order to have the sum part, and get Rails in case of none. And in the same question, there's an answer about from Runar. He's the guy from one of the author of functional programming in Scala, and he said, oh, you know what? I work kata. But anyway, long story short, no matter what we pick here, they all have the same complexity. It's exactly the same code that we are running. So behind the scenes, it's exactly the same. So you just pick your poison. That doesn't really matter. So where we are at, we have for data structure, the map with set of ints, we have side by side, the mutable and the immutable version. So the immutable implementation and the mutable implementation. We just propagate to the mutable one, the kata thing. It's very simple. So side by side, like this. So we have the immutable dog and the mutable. So it doesn't really matter. Now, why I put that? Sometimes, often actually, you find online like crazy shit. Like this guy that like thinks everybody can think whatever you want, but saying that immutable behavior could be dangerous, immutable behavior could be dangerous if you're not expecting it. For me, it's like, I have no doubt about it. By the way, you can have your opinion. I don't mind. So we have 2 implementations now, and now the question: okay, we solved the problem for map of set of ints. What if we change the map? What if we move from our map to this one with a nested map? Okay, this is our implementation. Now, okay, we change the type, but now the signature, but now we have to change the implementation nesting, looping. Yeah, we can do it. No, we are developers. We know how to do it. And what if we change the data map? What if in our system we have like 3 different data maps and we want to do exactly the same thing on those 3 data structures? Anyway, we know how to do it. We are a Scala developer. We're cool. We do ad hoc polymorphism. We create our trade. We notice that these types are exactly the same, so we can do the blend. We know how to do it. It's easy. You have a project with 100 data structures. You have to create 100 implementations, slightly different, all the tests. We can write very easily 1,000 lines of code per day. That means we can be extend developers. Ad hoc polymorphism, it's cool. It's cool. But no, seriously, we notice that there's something there. There is something. So if I want to do this on similar data structure, there is some abstraction there. Probably I should look at the root of what I mean with blending, because I came up with this blending thing, okay? You guys know already what I mean with blending with list and sets. Is the traversable plus plus operator. But what about int? Can I blend int? My world? Yes, we can blend int. Yeah, but wait a minute, what is blend? In my world, blend is the plus operator. So when I blend 2 ints, like 1 and 2, I want 3. Easy, okay? So we have int and plus. Same thing with string. In my world, blending 2 strings is like concatenating them with a plus operator. So we have the type and the binary operator there. And we did this already. We already did. With this map is a proper type. It's a proper type, so we have our implementation using the ad hoc polymorphism. Again, we are fine. There is a pattern here. We need to abstract. There is an abstraction. Of course, we can invent things, but to be honest, now we can see there's an abstraction. So we should look for something that is already there. Okay. So yes, there's something already there. There's plenty of things already there. Already proven. They already work. Okay. Wait a minute. Before proceeding, there are 3 slides about category theory. I know that somebody thinks that category theory is like snake oil. Just ignore those 3 slides, and then everything will be fine anyway, okay? So 3 slides. Semigroup, okay? This is the definition, one of the definition of semigroup. Sounds very cryptic, okay? But for the moment, let's forget about the blending problem. Let's think in the most abstract way here, okay? So at the end of the day, we have a bunch of things S, and we're gonna apply an operation on 2 of the things, and we get another things for the same bunch. Okay, let's keep going. There are 2 properties in that definition. Property number 1, closure. What I brought here is one possible implementation in Scala of a semigroup. Okay, and the closure property, it's very simple. It means that we have two things from that bunch of things, D, and we do something on them, and we get something as a result going through D. That's it. It's that simple. It's not the closure like closure compiler or the closure on the free. It's super simple. It's a mathematical closure, and there's a link here if you're interested about what a mathematical closure is. But it's that simple. Why it's cool with Scala? It's that we don't have to do anything. The type system will enforce this property. So by the fact that we write this, we know for sure that the type system gave us this property for free. Just an example, but we already got it. This hold, that property, this op here, in Boolean doesn't. It's super simple. It's not that difficult. Now, second and last property, associativity. That's slightly more different now, slightly more difficult. So we can't use the type system to enforce this, but that's basically what we can do. So you can see here, basically, we are applying to the first 2 and then to the third one, or applying the first one against those pair. It should produce the same thing, associativity. Be careful, that's not commutativity. So we cannot, okay? That's it. Now that we saw those 2 properties, this definition is not scary at all. It's like, if we read it again, it's super simple now, okay? A set with an operation that holds the associative property. Okay, so far so good. Okay, now we don't want to reinvent the wheel. The semigroup implementation is on millions of libraries. I just got Scala Z for whatever reason. And semigroup is there in the tech Classopedia. What that means, that maybe you didn't know, but every time you import things like that, you know, when you want to import in Scala Z all these goodies, like, yeah, I'm using a set, let's add that. You get a lot of things, including this. This is not actually the real code, it's adapted for this. It's very similar to what you can find inside the set, inside like this import. So what it does, nothing scary at all. It's basically saying, you know what, I have this implicit, and it's a semigroup of set of A. And this append is the operation that we saw in the definition. So it's simply implementing the semigroup with this logic. Look at that. If you import that thing we saw earlier on, the thing, we get the plus plus. Exactly what I mean for blending. So we're lucky. Otherwise, we have to implement our implicit. But the point is, when we import that set, we get the semigroup operation of plus plus with two sets. So far, so good. Let's use it then. We need to import another thing. We need to import this fancy symbol here, this fancy plus. So with the Scala Z syntax semigroup. And then, oh, sorry, this is a mistake. This is a set, shouldn't be a list. So you import the set goodies, you run this code, boom. What are you expecting? The plus plus operator, because the implementation we just saw. Okay? Now, list. We import the list stuff. We combine those two lists, like forming a semigroup together, and we get the same thing. Why? Because there is inside here, there is an implementation of list as a semigroup with that plus plus operator. That's why we get this. There's no magic. When you import that, you get also that implementation. Next, string, same thing. It does exactly what I'm expecting in my world. That's all for Scala Z? No, there's even more. Scala Z is so cool that has also this little trait. Very, very nice trait. This trait says, you know what? Semigroup has the associative law. And this is the implementation of the associative law. Do you remember? If we combine F2 and F3 and then F1 with the result, it should be the same as combining these two ones and then that one afterwards, okay? What's the power of this? The power of this is that we can import the Scala Z properties and say, you know what? Could you please tell me if the laws, the semigroup laws for int, here is the proper type you're gonna check, are holding. Because the closure is already held by the type system, all this Scala check code is just has to check the semigroup associativity law. That's it. What that means that you can pass whatever type you want. Okay? You pass all the types, you get all the tests. Scala check tests to check properties. I mean, if you don't think this is cool, I mean, you have no heart, to be honest. That's super cool. Okay. Oh, sorry. What we have here? Int of int? Yes. Let's try now our data structure, like that map with set of ints that we are, bringing over from the beginning of this talk. It works. Wait a minute, it works. That's cool. That means that I could blend those two guys in that way. Yes, because if you import the Scala Z map, you have in the append, in the semigroup operator, we have exactly the implementation you're looking for. He's expecting, that's an important thing, he's expecting two semigroups in the value, and he said, oh, I know how to do this. I just combine those two ones. That's the blender I'm looking for. Actually, this is way more precise than the blender I had in my head. Like, that's even more, it's like way more strict and it's like defined, clearer than what I had in my head. So that's the blender I was looking for. Okay, this is from, I adapted, it was from Monoid, I just adapted for semigroup, from the functional programming in Scala book. It says what, actually, as I've said, that sometimes semigroup, when are like nested, they could form semigroup, and that's a cool thing. Why it's cool? Check this out. I want to see you writing implementation for this. You have to write tests, you have to property test, all this stuff. We can use the the fancy like plus operator, and we get exactly what we're expecting after we define what blender is. Okay, it works like expected. Looks like magic, and I'm pretty sure. Don't be like virgin with me that in your code base you have structure like that. I'm sure because everybody has structure like that from some developer. So I'm not saying you should use it. I'm saying that everybody has these structures. Okay, that was difficult. Everything is done on the presentation now. It's like going to the end. Let's look with int. What's going on with int? In my world, int, when are blending together, they're summing. So, same key, what's the result? The value of a will be 3, okay? Why? Because int is a semigroup, and it's nested into map. And we know what map is going to do with the values. Options. Everybody loves options. Is this expected behavior? I don't know. Let's look at the source code. It's very easy. You have both sum. Check this. Look at that, man. This is the cool bit. Semigroup append. This is where he applied the ops, no matter what it's inside the option. If it's a semigroup, everything's a semigroup, and he knows what to do. Okay? With none, it's obvious. Go left and then right. The implementation is easy, but that's the cool part, I believe. Okay, very last example. We're almost there. Almost perfect. Okay. I want to do my semigroup with case classes. There's a question. Yes.
Sorry, in the previous slide, was it supposed to be a semigroup or monoid?
Yes, I was lazy, and this is exactly what you have inside the Scala Z source. I was too lazy, or probably I didn't realize. I changed maybe this to semigroup, or was already there, and we can check later on. At the end of the presentation, I'm going to check the source code. Yeah, but the thing is, because monoid are very similar to semigroup, in Scala Z they implement only monoid, and you get a semigroup for free.
Yeah.
So that's just it's just a detail, but you're right that you could spot monoid. And to be honest, yeah, the implicit the name doesn't matter, but that's the reason because they.
This one is actually very useful because that means if you have a semigroup or something, you always have a monoid of option of something. And that's when a monoid is expected, sometimes it's useful to be able to create one.
No. If you have a monoid, then you have semigroup. No, that.
Yeah,
No. If you've got a semi.
One second. Let's take the microphone. Which one? The left?
Yeah.
Oh, there.
So I just wanted to say that I find this one very useful because sometimes when a monoid is expected and you just have a semigroup, you can transform your semigroup of A into a monoid of option of A.
Yeah.
And sometimes that gives you the glue you need to get a monoid.
I almost there. It's the last
Yeah,
slide.
sorry.
Yeah, no problem.
But could you just move to the previous slide, please?
Sure. Yes. Okay, there you go. Now it's easy.
So here's the issue, right? When you define semigroup is a set with an associated binary operator.
Yes.
This operator has the semantic of plus for integer and append for int. But the set of integers also is a semigroup under multiplication. How do I make it
That's
work?
a good question. Okay, these guys in the front line, they asked me to remove 30 slides of this presentation, so I can bring some of the slides that explain exactly what's the question. It wouldn't be like 1 hour presentation, so they asked me to remove some slides. I have the answer. Yeah, for multiplication. Yeah. Short answer is you can use tag, or you can use another. So you can implement your implicit. But anyway, we see this later. Okay, let's finish this. Come on. Let's look at case class. You want to do a case class. Can we do a semigroup with a case class? Yes. So let's do a meetup organizer as a name, Jed, Mark, or Leonardo, Leo. And the meetup, Scala seed or closure seed. And then I want to do an operation. In my world, I'm going to combine meetup organizer with using the Yao community award int, okay? And of course, Jed won last year. Yeah. So how can I create a semigroup? It's very easy. Again, we just copy what Scala Z has done. So we create an implicit val, for instance, new semigroup, the meetup organizer, and then we just implement append. And the logic is very simple. It will be the left operand of the meetup organizer when we combine them, or the one that has the higher number of Yao community award. So, interesting. We want to use the Scala check inside Scala Z. So what I've done is I simply create the arbitrary for meetup organizer, and also implement equal, but that doesn't matter. And all I have to do, nothing yet, there's no trick, you can try yourself in the repo. I just call the laws of semi-group for meetup organizer, check, passed. If the logic here was like not holding on the associativity property, I would never ever pass this test, okay? So I think that's pretty cool. So now we have our semi-group for meetup organizer, and we can try it out. Mark and Leo, because Mark is on the left, we get Mark, okay? But when we have Mark, Leo, and Jed win, because the Yelp Meet Award. Now, it's a privilege, you know. No, seriously, congratulations. The thing is, that was not a joke. Anyway, very last thing before wrapping up, non-empty list. And okay, non-empty list, and we get all our subgroups, and then we call this sum left one. Doing that is exactly the same as this. Okay, these two are absolutely equivalent. So doing that, we get the same result, of course. Okay. So this is like the blender, and this is when we press the button and we blend multiple things together. Okay. Now, we saw how to do like a case class. Now let's have some benchmarking, because we have like here multiple ways to go to the first one. Okay, like in this image. So let's have a look at all the different implementations and how they performs. So okay, first of all, I did just one benchmark, so I'm gonna show you the result of the benchmark with that data structure, and about the set I'm using, the overlap between the two sets I set at 50%. So it's like a medium overlap. This code is already online, so if you look at my Twitter, I just tweet where the slides and the code is, so you can try yourself and try maybe different combination and see maybe different benchmark results. Here we go. So this, you can see here the size of the map. So we get up to 100K like dimension of the maps. And this is the mutable native implementation, the very first one, the one without the option, okay? And this is the immutable version. Okay, why is that? Of course, because with the mutable one, we had to convert from immutable to mutable, do our mutating thing, and then back to mutable, okay? Because that was the signature. So that's why it's slower. But one interesting thing is this. When we switch to option and use the kata, how is the mutable version using the kata? Yeah, roughly the same. And if you look at confidence, it's basically they're the same solution. And same thing with the mutable version. Okay, if you look at the confidence, they're basically the same. Okay, roughly. Now, question for you: what's going to happen when, without any implementation, I just import Scala Z and I use the fancy plus operator? Will be faster? Will be slower? Will be in the middle? Exactly the same as the mutable. It's exactly the same implementation. It's just fancier. It's that we're using the semi-group. You know, the semi-group is just the idea, but the code that runs is exactly the same. Yes, I'm promoting functional programming now, okay? I'm pushing for that. Okay, very last one, and then we're done. Let's say I want to change the signature. Instead of having immutable maps, I'm having mutable maps, and I'm returning mutable maps, doing a thing that you can do in your code base, and it's like mutating in place the map and returning the map mutated, okay? This will be, of course, will be faster, okay? It's up to you if it's fast enough for what you have to do, and that, you know, it's what exactly you want to mutate in place the map. What about the option? If you have any doubt that maybe using the kata and using the option could slow it down, actually, in this